Hey guys, welcome to EU Maths and let's do some maths for fun. Today, I will continue to prove Fundamental Differentiation Formula for part 2. In previous video, we have proved the first 8 basic differentiation rules, which will be used over and over again when we want to prove other formula. Alright, so let's get started. But before we start, we have to first understand the Squeeze Theorem and 2 special trigonometric limits. The Squeeze Theorem, it sounds interesting, right? But it is just about the limit of the function that is squeezed between 2 other functions. Oops, wrong animation. So for this graph, we can see that fx is squeezed between gx and hx. The Squeeze Theorem states that if hx is smaller or equal to fx and fx is smaller or equal to gx for all x in open interval containing C, except possibly at C itself, when 3 graphs meet at the point where x equal to C, then the limit will be the same for all 3 functions. It just doesn't seem helpful, right? Never mind, we'll move on to the special trigonometric limits. We have 2 of them. Now consider a unit circle. The radius of the circle equal to 1. So this point will be 1, 0. We draw a right angle triangle here in blue and label this angle with theta. So this point will be 1 tangent theta, because we know that tangent theta equal to opposite over adjacent. So for this right angle triangle, our theta is here. So this is opposite, this is adjacent. We can see that adjacent equal to 1. Therefore, tangent theta equal to opposite over 1. So opposite will equal to tangent theta. This is our opposite, so this will be tangent theta. Therefore, the coordinate of this point will be 1 tangent theta. Now I will color this sector with green color, then plot a point of cos theta, sin theta. Connect it with 1, 0. And now, we will have a circular sector which is squeezed between 2 triangles. We will now compare their areas. Upon your IBB and see, the blue triangle is bigger or at least equals to the area of the green sector, and this green sector is bigger than the green triangle. To compare their areas, for the first right angle triangle, we will use the formula area of triangle equal to half times base times height. And then as you can see from here, the base equal to 1. And then the height equal to tangent theta. So it will be half times 1 times tangent theta. Therefore, it will be tangent theta over 2. For the sector, we will recall back what we learned in circular measure. The area of sector equal to half r squared theta, where this is theta, and the radius still 1. So it's half times 1 squared times theta. Therefore, we will have theta over 2. For this triangle, we will use back the formula area of triangle equal to half times base times height. So the base still 1. A half times with a base is 1 times with height. What about the height? You can say that the y coordinate of this point is sin theta. So the height of this triangle will also be sin theta. When we multiply them together, we will get sin theta over 2. Now we have this very beautiful expression. We multiply the expression by 2 over sin theta. For tangent theta over 2 times 2 over sin theta, 2 and 2 can cancel each other. And we know that tangent theta equal to sin theta over cos theta times 1 over sin theta. Sin theta and sin theta can cancel each other. We have 1 over cos theta. Then for the second one, theta over 2 multiplied by 2 over sin theta. 2 and 2 cancel each other. We have theta over sin theta. For the third one, it's very simple. Sin theta over 2 times with 2 over sin theta. 2 and 2 cancel. Sin theta cancel. We have 1. So this is the expression that we will get. And now, we'll take the reciprocal of this expression. We have something like this. Remember to reverse the sign because the inequality used is now different. We can now apply the Squeeze Theorem from earlier. Finally, it's useful, right? So we'll take the limit of theta approach 0 of cos theta will be smaller or equal to the limit of theta approach 0 of sin theta over theta, and it is smaller or equal to the limit of theta approach 0 of 1. Know that cos theta equal to 1 from the graph of cosine, which is something like this. This is 1. And the limit of theta approach 0 of 1 is still 1. Therefore, we'll have this. Therefore, the limit of theta approach 0 of sin theta over theta equal to 1. And this is the first Trigo limit that we need. For the second trigonometric limit, we will multiply the numerator and denominator by cos theta plus 1. It is actually equals to the fraction times 1, so it will be the same. The purpose of this step is I want to use this identity, which is a squared minus b squared equal to a minus b, a plus b. As you can see here, my a will be equal to cos theta and my b will be equal to 1. So when we expand it, we'll have cos squared theta minus 1 over theta times cos theta plus 1. And now we look carefully at the numerator. It just looks so familiar, right? Recall back the Pythagorean identity. Cos square x plus sin square x equal to 1. Rearrange it. Cos square x minus 1 equal to negative sin square x. Now we can say that the left hand side is equal to our numerator. Sub in negative sin square theta into the expression, we'll get something like this. Next, we split the fraction into 2. Sin square theta equals to sin theta times negative sin theta, right? Then we will take the limit separately. And now you see the blue part is our friend, right? We just proved that it is equal to 1. And for this red part, we know that sin 0 equal to 0 from the graph of sine. From the graph of sine, it looks like this, so it's 0. So the whole thing, the whole red part will become 0. And 1 times 0 equal to 0, therefore it is 0. We can conclude that the limit of theta approach 0 of cos theta minus 1 over theta equals to 0. This is the second special limit that we'll need later. We can now proceed with our differentiation formula. So our target in this video is this 6th formula. But of course, we need to be familiar with all the add rules from the last video. So let's begin. Number 9, the derivative of sin x. By definition of differentiation, derivative of sin x equals to the limit of delta x approach 0 of sin x plus delta x minus sin x over delta x. And we recall our addition identity. Sin a plus or minus b equal to sin a cos b plus minus cos a sin b. So we will substitute this into the expression with green color. Now we will rearrange the expression. Then factor out sin x in blue, separate the fraction, factor out cos x and sin x. And then by constant multiple rule, we can pull out cos x and sin x when we take the limit. You see, our friends are here again. Just now we just proved that the blue color is 1 and red color is 0, right? So we will have cos x times 1 minus sin x times 0. And it is equal to cos x. Therefore, the derivative of sin x equal to cos x. Proven number 9. Number 10, the derivative of cos x. By definition of differentiation, derivative of cos x equals to this. And now we need the Trigo additional identity again. Cos a plus minus b equal to cos a cos b minus plus sin a sin b. Substitute into the expression in green color, we'll have this. Next, we'll rearrange the expression. Factor out cos x in blue, separate the fraction, and factor out cos x and sin x. Same as just now, we will take out cos x and sin x as constant, multiple Then we will take the limit of delta x approach 0. We will meet our two friends again. Red color is 0, blue color is 1. So we'll have cos x times 0 minus sin x times 1 equals to negative sin x. Therefore, the derivative of cos x equal to negative sin x. Proven. It may not be convincing like this, so this time I will do it graphically. Insert the graph of sine and graph of cosine. Cut it into 4 segments, 1, 2, 3, 4. Refer to the graph of sine. For the first segment, we can see that the value of y increases. So we say it has a positive gradient. However, we can also see that the graph becomes less and less steep. So the magnitude of the gradient decrease. Generally, we will just write positive gradient decrease. Therefore, the derivative graph will curve downwards above 0. And we just have to check the cos graph. We can see that it is true. For segment 2, the value of y decreases. And the curve becomes steeper and steeper. So, negative gradient increasing. Therefore, the derivative graph will curve downwards below 0. Check the cos curve, it will be true. The logic here is, if y increase, then we say it has a positive gradient. If y decrease, then we say it has a negative gradient. For the steepness, if it becomes steeper and steeper, then the magnitude will increase. If become less steep and less steep, the magnitude will decrease. This is true for all segments including segment 3 and segment 4. If we check the cos graph, it will be true for all of them. Does it make sense like this? Don't worry. It will all make sense when we are older. Number 11, the derivative of tangent x. We know that tangent x equal to sin x over cos x. So derivative of tangent x will be the same as derivative of sin x over cos x. Point your eye, B, B, and C. This is a quotient, right? So we will use the quotient rule. Let u equal to sin x and v equal to cos x. Thus, du over dx equal to cos x and dv over dx equal to negative sin x. Write out the formula. Substitute v equal to cos x. Du over dx equal to cos x minus du equal to sin x. dv dvx equal to negative sin x. And now we will see our another friend again. This is the basic trigon identity, remember? So the numerator will be equal to 1. We have 1 over cos squared x now. And it's equal to secant square x. Therefore, the derivative of tangent x equal to secant square x. Proven. Number 12, the derivative of cotangent x. This one is quite similar to just now, but this time, cotangent x equal to cos x over sin x. So the derivative of cot x will be the same as derivative of cos x over sin x. Apply quotient rule. Let u equal to cos x and v equal to sin x. Thus, du dx equal to negative sin x and dv over dx equal to cos x. Write out the formula. Play mix and match. Expand the bracket. Wait, who is this? We can factor out the negative sign by writing like this. Plus cos square x. And this is our old friend again, is equal to negative 1. So it's equal to negative 1 over sin square x. And it is negative cosecant square x. By the way, CSC is the same as cosec. And both of them are short form cosecant. Okay, don't get confused by this. Anyway, the derivative of cotangent x equal to negative cosecant square x, and we have proven. Number 13, the derivative of secant x. We know that secant x equal to reciprocal of cos x, so I don't want to read this again. Open your IBB and see, it is still a quotient. Apply quotient rule, let u equal to 1 and v equal to cos x. Thus du dx equal to 0, dv dx equal to negative sine x. Write out the formula again, place substitution again. Simplify, we'll get sine x over cos square x. But I don't want square. I don't want this square. I want 1 over cos x. Because 1 over cos x is secant x. And sine x over cos x is tangent x. And this is the derivative of secant x. Number 13, proven. Number 14, derivative of cos secant x. She is a friend of sine x. So when they make up, they will look the same. Apply barbecue cream. Let u equal to 1 and v equal to sine x. Du dx equal to 0, dv dx equal to cos x. Write out the formula, fill in the blank, say goodbye to sine x and cos x will become set at negative. I don't want square, don't want negative. And finally, we will have negative cosecant x, cotangent x. And this is the derivative of cosecant x. Number 14, proven. As for today, we have proved derivative of all 6 trigonometric functions. We only left logarithmic and exponential function. Progress today. Almost done. Alright, thank you for watching. See you guys in the next video.